Hello, everyone. You're welcome to the Gallogly College of Engineering Graduate Student Community Program today. So we always have like a webinar series, and our speaker today is Professor Zhang, who is an associate professor in Purdue University. So I'll just give an introduction of our association and how to join our association before we give the floor to our speaker. So the graduate student community has like a leadership team, and the leadership team this year, the co-chair are Rodney and Rachel, and we have people in charge of our publicity. We have like different program like the International Food Evening, the faculty mixer that we have to publicize, and we have the treasurer and also like a group of support from all departments in the College of Engineering. And our mentor of our association is the ever efficient Professor Mystery Farouk. And we always have like our meetings. The meeting for this semester holds on Friday at 4 p.m. And this meeting are also, are usually held on Zoom just to allow flexibility for everyone. So if you need like the meeting link and also for question regarding the meeting time, you can always contact Rachel or Rodney. And every semester, we usually set like the time for the meeting based on the schedule of the attending student. So it's Friday at 4 p.m. is not fixed for all semester. It's flexible. And to become a GSC member on Engage, so what you have to do is you just need to scan the QR code and log in with an OUID, then click join, and congrats, you are a member of our GSC. And we also have a group on LinkedIn where we have like our members join. So to join the group, you can scan this QR code. So in the group, we share like opportunities and also different posts for professional development of the graduate students in the College of Engineering. We also have a Facebook page where we used to, advertise our programs and different programs that we organize. So you can just scan this QR code. It should take you directly to our Facebook page to get an update on our activities. And also, all the webinar series, we usually host them on YouTube. So in case you miss like anyone or you want to make reference to any presentation that you miss, you just need to scan the code. It will take you to our YouTube page. So you would see like, different our different webinars that we've been hosting. And one of the resources that we have for our graduate students is also the Dave and Bet's team room, so which is in the engineering laboratory. So we have different amenities like the couches, the whiteboard, coffee pots, microwave. And if you need access, you can just email Professor Farouk or Rodney to gain access to the room. And reminder, so a link of the Google form will be sent in the message. So you can just help us, sign the attendance for the program for this. And today, our speaker is Professor Zhang, and the title of our presentation will be Physics Informed Simulation Model for Advanced Composite Manufacturing. So I would stop sharing my screen now for Professor Zhang to presentation. Thank you very much. Yeah, I think Professor Zhang, you can share your screen now.
Sure.
Yeah, thank you.
Can you see my screen?
Yeah.
Right. Thank you very much and for the invitation. And it's truly my pleasure presenting my work on the physics-based simulation model for advanced composites manufacturing. And my name is Dianyun Zhang. I'm associate professor at School of Aeronautics and Astronautics at Purdue University. And I realize we have very diverse audience today, not particularly working on composites or materials, but also we have seen lots of nowadays the research is focusing on AI machine learning. So I wish what I present will be interesting to you, and hopefully we will also explore some of the collaboration opportunities that you could see now the AI machine learning are being used also in the composites manufacturing simulation as well. So before I started, I also want to have a brief introduction for our composites manufacturing simulation center. So I'm employed by the Aerospace at Purdue, but also affiliated with the Composites Manufacturing Simulation Center. The center was established in around 2016 with the support from Acme and to develop industrial collaboration with supply chains and OEMs to advance manufacturing simulation for composites. So over the years, we develop a partnership with a variety of different industry companies, including Dassault Systèmes through their 3D Experience Education Center of Excellence in Advanced Composites. So we kind of leverage the advantage of getting full access to the software. And we also have the partnership with Thermood to develop larger scale additive manufacturing. So you can see the movie at the corner. So that's not really 100% my research, but we actually share the facility and develop lots of interesting collaboration work as well. Over the years, we been also working on the high rate composite manufacturing and practice the model-based engineering. So I know some of our audience is from industrial engineering. That's probably you're familiar with the word model-based engineering to do a composite manufacturing using platelet system. We also have a very interesting platform. As you can see, the middle photo has the cloud is the CDM hub. So this is a cloud-based infrastructure, allow researchers and the educators to share teaching resources, research resources, and the most important is the codes, the simulation codes for the entire community. So if you are doing nano research, I don't really know if any audience are doing that. You're probably familiar with the Nano Hub. So the CDM Hub is particular for composite manufacturing simulation. So if you would like to know more about composites or want to get more teaching resources, you can go to the CDM Hub. So the goal is you can also publish your codes, and then people can actually run your codes on the cloud without installing the codes locally in your computer. So this is there are lots of interesting resource on the CDM Hub if you are interested in. And with the center focusing on composites manufacturing, we also have a variety of different facilities available to support composites manufacturing, including the autoclave, the press for the compression molding, and a variety of the machines allow us to do materials characterization, mechanical testing, and also laser scan allows us to measure the part dimension after the manufacturing cycle. So you will see some of the application of those equipment for the to support simulation work. So since most of you probably not really familiar with the composite, you probably heard about the name. This is a material being widely used in the aerospace structures because of the weight saving they can provide. So the general idea behind the composite is you want to combine multiple materials and to maximize the benefits of each of the material. So if we look at the composite, it's a combination. The composites I've been working on is the combination of reinforcement and binding. In the particular, we are looking at is we're not just looking for the carbon fiber, but most of the research I've been working on nowadays is more using the carbon fibers because it's very strong and stiff. But one of the drawback by using simply carbon fibers, and we know carbon fibers never been in a structured material itself, is because it's very brittle. And also it's very difficult to handle because it's just like your hair, it's fairly small. So to make it as a structured component, you also need a binding polymer, which we use in resin to bind the reinforcement. And with the hope is that we can get a one integrated part and with the stiffness strength we love to have, and also have better damage tolerance because the resin system had larger strain to failure, so it's more ductile. So mainly we want to add ductility to the carbon fiber reinforcements and to create a composite. And towards the manufacturing process, there are a variety of the manufacturing process we can use to make the composite parts. We will start by talking about the liquid composite molding, since this is the manufacturing process I have been focusing on for a while. And later in this talk, you will also see the advanced automated fiber placement that we use in robot to making composite parts as well. So if we start from the liquid composite molding, this is a process that's very suitable either on the like a high rate, low cost manufacturing, or it be used for the parts that with pretty complex geometry to use the liquid composite molding. So it usually started by you lay down the mold. So the mold not necessarily being flat. It can be any of the contours if you need any geometry you are looking for with the parts you want to manufacture. And then you lay down, we call the reinforcement. Those are the fiber preforms over the mold. And then what we do is we also need to close the mold. And when the first process is we just drop those dry fibers over the mold. So we call this as a draping process. And after that, we will need to provide some compaction to compress the molds, and then do a resin infusion process. So during that process is the binder, the polymer being infused into the dry preform. And after that, you need, we call it a curing process, because this usually is for the thermal set. So we apply a curing cycle. This is just like when you're dealing with your epoxy, right? For any of the repair project you are working on. Some of the adhesives also require a temperature cycle for the curing. So we will need to apply the temperature, and once we allow the resin to be fully cured, then we reduce the temperature and do a demolding process. So from that, we expect to get a fully consolidated and cured part for the composite part. So because of this manufacturing process, we also see beyond we just see a advantage of using composites is we also see the defects. So those defects can come from the infusion process where you can see there are dry spots. There could be like a dry spots, which means the resin or the polymer never reached that area. So there can be something wrong with the infusion process. There are cases when we do the forming of those dry fibers, the wrinkle can occur. So especially when the geometry of the mold is very complex, we will expect to see the wrinkles. And there are also cases where we see those, it's maybe not very significant, but if you pay attention, I think with the zoom, you probably can see from the screen, is there are actually also cracks developed. So those cracks is not because you apply mechanical loading that to break the part, is because the curing process generates lots of heat, and that heat can introduce large enough residual stress that eventually develop micro cracking in the polymer. So at the structure level, we also see the dimensional change, which is very significant for the manufacturer who have, especially for the material being used in the aerospace application, it requires very tight control on the dimensional stability. So there are cases where because the material anisotropy, we expect to see the warpage in the part if we try to stack in two different orientation of the fibers. Or there are cases we also develop what we call the spray in of the part, which means we want to do a 90-degree bracket or the flange. So if your mold is perfect 90-degree, and then like the process as I described, we drape those fibers and do the infusion and curing. Once you do the demolding and then you measure this enclosed angle, it is no longer 90-degree. It will actually, we call the spray end. So the enclosed angle will actually being decreased. So it was always around like between 1 to 2 degrees spring angle. So the question is, can we really predict, or what really caused this spring angle, so that we can do the mold compensation, so that we can get exactly 90-degree bracket. So this all coming towards the question is, can we have a numerical simulation to guide us for the manufacturing process, with the hope that we can develop digital twins for the composites manufacturing. So this kind of be the work that I have been working on in the past several years, is to look at this liquid composite molding process and trying to have individual components being simulated, and also to explore the physics behind it. So it all starting from the fiber draping, right, which is where we want to have the reinforcement follow certain geometry that depending on the geometry you are looking for the part. Then there will also exploration about how we do the infusion process. What caused the defects, right? Or can we navigate, or is the simulation can allow us to understand, if I doing this, yes, you do expect to see some of the defects in the part during the infusion process. And then once the infusion process being finished, then it will be a thermomechanical analysis, allow us to understand how the residual stress will be developed, and eventually how that affect your final dimension, and how that being linked towards the strength prediction, right? So, because at the end of the day, we really wish to see if we know the performance of the part while we are understanding the manufacturing process. So this breakdown it to individual physics-based approach to understand what is the how to simulate the draping, what is the fundamental mechanics behind this draping simulation, then the infusion process, and also the curing process. So we do have each individual simulation framework being developed based on the physics behind each of the manufacturing process, each of the step, and eventually link towards, we see how nowadays the AI machine learning will help us eventually move us towards the digital twin for composite simulation. So if we are provide some of a very quick discussion about each individual process, and you will see how eventually everything being assembled together. I know there are very few audience is working on mechanics. So when we're looking at actually the fiber draping process, this is essentially a process that being really focusing on the mechanics itself. So especially the case when you expect to see the draping process, it's a fairly large deformation that being involved in the entire the deformation of the fabric. So with that work, one of my students actually working on having a physics-based hyperviscoelastic simulation framework to capture the when you actually try to place down your fabric over your mold, how to efficiently predict the fiber orientation. So this is some of the work that we've been working on to have a very robust fabric model to predict the fiber orientation when it is doing the draping process through the framework of the hyperviscoelasticity modeling framework. Then once we know how the fiber, the draping process, we also need to see if there are ways we also passing that information to the infusion and also the curing. So over the years, we also working with a small company, Global Engineering Materials, that to develop a more smooth integration of also the infusion and the curing simulation itself. And if we look at each individual simulation on the infusion, we need to incorporate whatever the architecture of the textile and also the flow compaction phenomenon into the infusion process, and get a leverage the external database so that we can pass in information from the infusion, which is carried out by the CFD simulations, pass it towards the FEA simulation so that we can do the residual stress analysis on the part and allow us to predict the the dimensional change, also the stress distribution at the end of the manufacturing cycle. So some of the very interesting work that we are been doing is it all starting from some of the validation. So we still use a pretty engineering approach by homogenize the entire infusion process to based on the Darcy's law. So basically we treat those preform as a porous media and to see how the flow passing through. So on the experimental side, we need some of the experiments that we are actually need to characterize the permeability of the fabric for our simulation work. Then we also run a benchmark study to and trying to see if we can do some of the benchmark study to simulate the cases where this is L bracket or the ones I shown in the middle is the simulation flow for a doubly curved mode, or the infusion for a semi-hemisphere shape, though like kind of the dome shape. So once we kind of validate those simulations by taking the results from the fabric characterization, the next step is we want to further explore. Some of the things, and you will see while we are looking at the entire simulation workflow, we really focusing on the integration, right? So one of the things we also realize is we see so many defects during our infusion, even as simple as a rectangular bracket shape, right? You will feel kind of like easy that you put resin in one we have the resin infused on one end and the suck out on the other end. We expect to have a very smooth, as we indicated on the original simulation, that the white line is actually showing the movement of the resin flow front, right? So we do expect to see pretty smooth, right, behavior. But unfortunately, this is not really something we observe in the most of the time when we see in the lab. So if you see this movie more closely and compare with the ideal case of the simulation, the main difference is when we see this behavior, we see the acceleration of the resin flow front at the corner. And this is pretty common. We have seen this multiple times. So when we go back towards our simulation, we know only simulate simply assume that this is porous media adding some permeability to simulate the resin flow front is not really sufficient. One of the phenomena behind it is the compaction force. The compaction will affect the permeability as well. So then that triggers to look back towards our fabric model to really understand what are the compactions will happen at the corner. And we realize from the fabric simulation, it actually has we definitely expect that the thickness at the corner being slightly thicker than the edge of the panel. So we have to account for the fact that the compaction force will affect the permeability, and incorporating that effects into the simulation so that we actually capture something very similar to what we see from our experiment. I mean, this is something very interesting because we have been talking about defects so many times. What we observe from the experiment is if we got acceleration at the corner, the flow get accelerate, and if you look carefully about the top corner, it enters with some of the dry spots because the resin is very hard to penetrate, flow to that region and only being wetted by diffusion. So that will be very slow process that can fill that dry spots. And this is also something we observe in the simulation, that if we got acceleration flow because of the compaction force is small at the corner, it increased the permeability. The resin got accelerated, and that can with those L bracket, it can got the dry spot on the one of the flange. So once we have the capability to simulate the recent flow, the next step is we also need to looking towards the curing process. This is also more tricky because it kind of combine the chemical reaction with a heat transfer phenomenon. And eventually, we have to capture all the key mechanics associated with this process and allow us to know what's going on. So there are actually two key elements. One is we need to know for this material is the thermoset polymer when it's doing the curing process, what is that chemical reaction, how the polymer behave itself. The next question is, now we also have reinforcement, right? So we also need some ways to do homogenization to account for the microstructure effects and the architecture effects of the reinforcement as well. So there are two things we have to work on. So on the heat transfer perspective, we know the curing process is a exthermic process. You will expect if you wait your adhesive or the super glue to cure, you feel the part become warmer, right? So because the heat will be generated during the curing process. And that heat generation will be characterized using cure kinetics, which we can measure we can measure that cure kinetics in the lab using the device in the lab. On the other side, we also need to know how to incorporate those cure kinetics into the stress analysis by understand how the constitutive behavior how the polymer evolve, right, during that curing process. So I know most of you are not focusing on the mechanics, so I will try to keep it brief. But as you can see from the diagram, we actually have to see the transition of the polymer into the different stage during the curing. When we do the infusion process, it's just like a liquid, right? So we actually have to carefully monitor the viscosity change, because when the viscosity is suddenly being increased, we know it will pass the gelation point. After that, the polymer no longer can flow, right? And then it will in a kind of a rubbery stage where the polymer start to develop cross-linking, so it start to form the stability, the stiffness, but at the same time, it can also have a huge capability to do the stress relaxation. So we have to treat this as a viscoelastic material. And at the end of the day, when the crossing the vitrification point, which is the in-situ glass transition point, and it's where it develops the final stiffness of the part. So but it also being considered here is because it's also under cooling, right? So mainly the polymer being get to finish the chemical reaction at a relatively high temperature and then cool down to build up a stiffness. So in the whole process, we have to account for the modulus change as a function of time, degree of cure, which is your curing process, and also have to account for the thermal strain and the chemical strain, because when you form those cross-linking, it actually will shrink. So those things need to be considered into the modeling framework. And also, as I mentioned earlier, is the reinforcement, right? How we need to do the homogenization. So there are ways, get more detail about how to actually incorporating all kinds of the phenomena I just described into this thermal viscoelastic framework. And another thing we have to focusing on is the homogenization, right? Is how you bring in multiple length scales together. So this is also the way that we looking at the micro scale to look at the individual fiber measure scale to do the micro scale analysis. Then we also need something with the mesoscale simulation framework, and all the way towards the macro scale, which we need a way to homogenize at the end of the day for the structure analysis. And we also get a very efficient way to develop a thermal viscoelasticity framework. This requires some of the mechanics work involved by leveraging some of the existing model for viscoelasticity, but also adding the thermochemical part for the curing part, and we also have to account for the microstructure effects. So we also have that framework in place so that we can simulate entire curing process. So when we are putting together, this is pretty comprehensive model as we are looking towards how we trying to have only the fiber, the matrix process at inputs, and with the outputs towards how the part will deform and how the overall behavior of the structure, right? So once we have this framework, one of the very interesting thing, I think, since we have so many audience from industrial engineering, right? This is kind of your word is now I have this physics-based approach by with the inputs as the material properties, basically your fiber property, your polymer properties with the processing uh, dependent properties, but we also have the processing parameters and also the geometry of the tool and the parts. Now we can put together as a optimization work, depending on what we really want to optimize and how we actually can tuning around our manufacturing process, right? Remember, as I mentioned, when we are doing this manufacturing process, one of the very critical step is curing. And so when we say it's a cure cycle, basically it's a temperature cycle you apply to your part. So with that, if we consider that is the if you see the red curve is the cure cycle we need to prescribe for the composite manufacturing, then the question is, can we actually optimize this cycle based on the performance we want to improve, right? So usually when you are working with the composite manufacturing, we will get a manufacturer recommended cure cycle from the manufacturer that is usually optimized for the material itself, but not necessary for like what you have in the in your part, right? For the real part that you are working on. So if we look at this whole framework, one of the question is now we are building all the physics-based simulation in our FEA software. We use the commercial software Abacus with user subroutines for the curing kinetics. Then we can link that with whatever the optimizer we have. So for now, we actually leverage the optimizer in MATLAB. You can use Python, whatever other language as well. So we are now writing our optimization algorithm. We leverage the existing optimization algorithm, but we get a way to link towards the physics-based simulation. So this is actually one of the example that we have is one of the goal we are trying to do is we want to optimize this cure cycle by optimize the heating rate. Then this is a polymer required, as you can see, as we call two-stage heating, that we ramp up one of the intermediate temperature, we holding for a time for a while, and then we ramp up a temperature again and holding for another duration of time, and then eventually cooling down. So we can look at the different heating rates, the time for the dwell time for each of the temperature we want to hold, and also the cooling rate. And with the goal, and if we look at, remember the L bracket example we've been talking about before, the goal is there any way we can tune it around with this cure cycle so that we can reduce the magnitude of the distortion from the by tuning around the cure cycle. But if you only have a single objective, it can also turn in your cure cycle being unrealistic, right? So not just like we want to minimize the spring angle and being at the same time, we also want to minimize the processing time, but we also want to maximize the degree of cure to make sure that your polymer is fully cured. Because if we now have a holistic thoughts on what we want the objective is, then it can come in towards a fact that yes, we reduce the spring angle, we reduce the processing time, but the polymer is uncured, right? So we need to consider all the pieces together and try to see what will be the reasonable approach. So we are still working on that on the final experimental validation to wrap up that piece, but we are very proud of having this framework being work because this is just one of the example. There are so many different pieces we can look into towards how we can optimize the manufacturing process to reduce the residual stress, to reduce the defects. Another thing we are also looking into is the uncertainty quantification. So one of the challenge with the composite manufacturing, and that's also one of the reason why people from the industry pushing for a modeling effort is what you see from the end of your manufacturing process is the part not always showing the same spring angle. Your spring angle can vary from day to day from the different people doing the manufacturing process, or due to the polymer variations that the batch you receive could be different, can be slightly different, and that can all contribute towards the defects or the variability you will observe at the end of the day. So this also towards some of the work we've been collaborating with folks doing AI machine learning is to see, hey, we're building this physics-based model. Can we efficiently predict the uncertainty propagation or the uncertainty in this manufacturing process? Especially here, we use the predicted spring angle as one of the measurement to see the variability. So, and also trying to also to answer another important question is, where is this variability coming from, right? Is how we go from micro scale all the way to the structure level, how the uncertainty will propagate. So this go towards some of our collaboration work with Professor Jiang Tan group at the University of Connecticut to understand the uncertainty propagation. And we have been collaborating not just on this single activity, we've been collaborating on a variety of things when I was at the UConn about how to looking at the different uncertainty propagation in the composite manufacturing process. So another goal of doing this physics-based simulation is at the end of the day, we want to exercise this with so-called ICME approach, right? The integration of the computation and material engineering concepts so that we can predict what we see in the manufacturing process and link that to the structure prediction. So that's also a work that we've been looking for in this area. So given my own background, I got my PhD on progressive damage for composites. So I've been learning the composite manufacturing when I was a assistant professor at the UConn. So I know some of you are at the end of your PhD and looking to your probably looking for jobs or maybe think about a faculty job. I mean, this is not the end. I mean, when you finish your PhD, it's not the end of your learning. It's probably just a start because I learned all those new things in composite manufacturing when I was an assistant professor. I'm still learning. I mean, we have been, you will later see some of our current work on more advanced composite manufacturing framework. I'm still learning nowadays. So one of the things we have to do is how to couple those residual stress predictions, defects, into progressive damage. So we also have to take lots of modification we did before for the progressive damage, and now we have to incorporating the residual stress and to make sure the convergence to solve the convergence issue, and also to make sure that the residual stress and the wattage being considered in the right way. So this is one of some of the examples we've been demonstrating is remember, we are actually fabricating those like a L shape, right? We actually do the real manufacturing process now. So we do have those manufacturing coupon. And so we actually know we can now have a better understanding about everything happened with this coupon. And now when this is actually ACM standard experiments to do a 4-point bending of this L coupon, and with the bending force being applied, we do expect to see damage or the failure delamination happen at the across the thickness of this composite panel. So the question is, should we, is that important to account for those manufacturing induced defects? And the short answer is yes. So it's actually being showing that there's lots of value or the importance of to incorporating those manufacturing-induced defects into the simulation workflow so that it will allow us to have a more realistic prediction and also have a better understanding about how those manufacturing process eventually causing the residual stress and also affect the performance of the part. So I think this whole holistic approach is kind of to demonstrate this idea. This is also more towards a smaller scale simulation. Is we look at the micro scale to see how the residual stress being developed, and eventually it will drive the failure in the at the micro scale, and that will also affect our prediction on the overall strength of the composite part. Important to do the physics-based simulations. This is kind of the work I've been working on for a while, but it's also very important to know can we also realistically measure some of the phenomena we capture in the simulation, but maybe not obvious from your naked eye. So we need some more advanced sensors to do the in-process in-situ process monitoring. So here we particularly looking towards the fiber optical sensor and the dielectrical sensors to do the process monitoring. If you are not familiar with the optical fiber sensor, it's just like a small hair that you can embed into your specimen. So it's like your strain gauge, but it's small enough that it can penetrate into your part. So you're now creating horrible defects in your part, but it gave you some of the measurements. So something you will observe here is this is actually we call the pre-preg, which you already have the polymer in your fiber, but we actually try to insert the optical fiber sensor transverse to the fiber. So we kind of measure, we call the polymer dominated behavior. So something we actually observe from the optical fiber sensor is that there's indeed a shrinkage that occurs while we have our constant temperature, right? So as I mentioned earlier, when we have those model, we've been talking so many times about, hey, you will have the chemical shrinkage because of cross-linking. And we indeed see that from the fiber optical sensor. And definitely you see the strain being developed because of the cooling. That is more obvious. But the chemical reaction also can induce the shrinkage as well. And we also have those dielectrical sensor that allow us to actually measure the flow front and also the in-situ curing behavior. So this become also very neat as now we have the sensor data that we can collect in process, right? Can we connect that sensor data to our physics-based approach, the physics simulation to do real-time prediction, right? This is also some of the motivation for the digital twin is can we link the real-time data to the prediction. So that's also to give us, now we kind of build all the foundation and trying to move to this digital twin idea for composites manufacturing. So with the last couple of minutes, I also want to quickly show the work on the automated fiber placement. So, well, lots of time you will see the composite manufacturing process is pretty labor intensive. Now we have the robot to help, and one of the real benefit is even composites have been developed and being used for a while, right? Being developed in the 50s, 60s, and we see a lot of application from 80s. Now we've been seeing that being used a lot nowadays. But if you look at the angle of the fibers being used, it's typically just a 0.90 plus minus 45. Sometimes you will see 30 or 60s, but you never see any mystery angle, right? Like a 37 or 21 degrees, because from the manufacturing perspective, this is not something you can easily control. So now with the robot, we actually can lay down the fiber precisely on the orientation you want to lay down. So it's very cool technology nowadays. So this is also one of the example I just showing a demonstration is, remember earlier the presentation of this double curved mold? Actually, this mold is 3D printed, additive manufactured from the lab across our hallway. So we will see how the additive manufacturing during the mold, and now we can lay down the continuous tape over the mold, which is very, very cool. So with this technology, we actually, you can see this is the movement of the tape that being wrapped over on the a double curved mold. So this is also a very, very neat technology that we've been using. So one of the difference in this technology is because we need to establish some of the techniques of the tape when we do the placement. So we also been looking towards what will be the right heating, what can be used. So using the IR heater is pretty standard for this technology, be working with the thermal set. But there's also a very cool heating device we also are installing is a Harrier Hum 3. This is not something like a laser, which we need lots of protections and lots of time we hit lots of the roadblock in the university facility to install laser. So Hum 3 is more intermediate heating power that is more powerful than the IR heater, but not as intense as a laser that we need all the protections. So it's still a flashlight to have a heating capability. So there's still lots of things machine parameters we are working on. But the very cool thing about that is this also allows us to do the placement of thermoplastic. So if you think about the thermoplastic, lots of plastic material we are using on the daily basis, thermoplastic, which means it's a solid at the room temperature, and once you reheat, if you heat beyond its melting point, you can reform it, right? In today's world about the sustainability, we have been pushing a lot for the thermoplastic materials, thermoplastic composites, due to the capability for the recycling. Thermoset composites, we still have lots of trouble for the recycling, but the thermoplastic composites, we have a way better capability to do the recycling. And this Hum 3 technology is actually allow us to lay down those thermoplastic tape using this technology. So at the end of the day, we are still trying to build a simulation for this automated fiber placement, right? There are also defects associated with that. It's a very cool technology, but even in the industrial scale, the TRL level still being rated pretty low. Even the technology itself has been around for more than 10 years, so probably close to 20 years. But still, aerospace companies are slowly moving to this technique just because the TRL level. It has been, if you've seen all the robot being used, that is for the tape placement, which you lay down the larger tape, not individual fiber tape. So this is our ongoing work to building also the simulation capability for those tape placements. So again, it will not just the mechanics, right? It will be combined with the heat transfer, the heating elements, all kinds of things into the simulation framework. One of the advantage of that is with this highly controlled robot arm, we also have more sensors that can be installed to do in-situ monitoring. So at the end of the day, it follows similar idea that we built for the liquid composite molding simulation. So this is also the preliminary work, as the wrinkling the major concern in this technology. If we trying to place the toe over a highly contoured surface, the tape now stay and will have the wrinkle. So I think at the end of the day, what we are moving towards is to building all those efforts together, learning a lot about the robotics and how this machine will work. And at the end of the day, we want to connect the physics-based simulation with the data sensor, and nowadays with the AI machine learning tool, eventually to build the digital twins for the composite manufacturing, and also moving towards a more sustainable approach, right? With the use of the thermoplastic composites and the robots to this system to reduce the waste we also make the composite manufacturing more sustainable and more environmentally friendly. So with that, I would like to take questions. I think I'm on time, right? You give me 50 minutes.
Yeah, thank you, Professor Zhang, for the
Thank you.
wonderful presentation. Actually, it's actually very cool. Yeah, it's actually interesting to see how, what goes into developing like physics-based model for like composites manufacturing. And yeah, so we'll try and open if you have any question for Professor Zhang or you have any comment, you can just like raise up your hand and yeah, you can just indicate, not raise up your hand.
I have a quick question.
Sure.
So first, of course, thank you for your presentation. It was really informative and
Thank
interesting, especially something that's not normally my what I work with. But with that, I'll say my last job was in manufacturing of gaskets and seals, like rubber materials. I was wondering if you think it could be adapted for molding like rubber hyperelastic materials like that.
Right. So this is a very interesting question. So several years ago, I got a project from with a Ford Motor Company, and that particular look at the rubber. So there, I'm not sure if it's the same rubber. I know it's probably slightly different, but those are the cooling holes in the vehicle system. So we got actually a couple of cooling holes, small and big, in our in the engine component, one of the engine components in the vehicle. And with nowadays, you try to get your components smaller and smaller, right? And one of the
Hmm.
issues is rubbing, because those rubber over time get creep and deformed, especially when the vehicle is under vibration. So that's actually the first time I get involved with hypervisco hyperelasticity, and eventually actually it always showing hyperviscoelastic behavior. So that's exactly how I get into that area, knowing how to do hyperviscoelasticity. Um, I think it's around probably 2017, 2018-ish. And so I learned from that and then incorporate into some of the simulation work later I did for the composites manufacturing. But yes, so very similar issue. The mechanics is slightly different. I made some mistake at very early of that project because I treated the rubber the same as a composite. It's a composite. It's reinforced by the Kevlar fibers, but the mechanical behavior is slightly different. But yes, you get very similar issue. It's just the fact that for the rubber components, they do not have that dimensional control as we see in the aerospace parts. So yes, you always get those like a dimensional change, but as far as the manufacturer know the tolerance, they just follow the same procedure. The challenge with the composites and why the modeling effort usually pushing from that end is, first of all, is the tight control, right? The tolerance control for the dimensional stability. And also the composite provide more flexibility on the design. Every those part, you can have different fiber angle with different layup that will give you a different spray angle. So you kind of have an endless try for what happened if tomorrow um the OEM decide the aerospace OEM decide to use a different polymer, a different fiber, then all the experience from the manufacturer gone. They have to do trial and error again. So that's why the modeling being pushed a lot in the aerospace just because of the nature of that industry. The rubber will face the same thing. It will still get the dimensional change. It will still have those residual stress um, issue, but usually the manufacturer, it's they're okay with that. They feel they may need a model, but it's okay without a model. But so it's very interesting when you look at different industries. But yeah, but like for a company like a Ford, they are important. To them, that is very important because they know the mechanical performance. And yes, if we can also help to build a model, say, hey, I know I can build in that manufacturing effects into the performance prediction. I think that would be wonderful. But unfortunately, I never got opportunity to do that. But yes, I do working on that rubber. The hyperviscoelasticity is very interesting phenomenon to study.
Yeah, thank you. Yeah, the reason I asked was we had a seal that was had Kevlar fiber woven through it, and then silicone or maybe FKM impregnated into it.
Yes.
Um, yeah, for an aerospace project. But thank you for your answer.
Yeah.
Thank you, Rodney. My question for Prof. Zhang is, when you have like those models that you talked about, like the failure model, the viscoelastic model, and the multiscale model, so how do you go about like the experimental validation? And what are the, for different model, what are the validation metrics that you use to compare like your simulation result
Right.
to experimental? Yeah.
Right, this is an excellent question. So I didn't get time to talk all. But this is extremely important. And as you will see, when we thought we are a composite manufacturing simulation center, we all agree that we need lots of experimental facilities, right? It's for the validation. So I think this is actually a challenge. There's no standard. There's no we wish maybe one day we will conclude with some of the standards, say, hey, these are the characterization, those are the validation you should perform. But unfortunately, there's no. As I say, my PhD was in the progressive damage. We know with all those structure failure prediction, we have ACM standard, right? So we know those are the experiments we need to do. And also in the literature, there are huge publications about, hey, those are the experiments, those are the ACM standards you need to follow to validate your model. But there's literally none in the manufacturing world. So what I learned from the composite manufacturer is that internally, definitely they never share me the details, is internally they have built a certain coupon level validation case. Say before they fabricate the larger piece, if it's the first time they using that resin or they use that fiber, they have internally building smaller case to know the process so that guide them to design the larger complex structures. I'm pretty sure the L bracket is part of it. So for us, it's really, I would say we don't really have a very good ways to do that. Like we do some very simple case, like for example, if we look at the draping, we do the hemisphere, try to measure the fiber angle to see if we can predict that. Or we do individual toe shear and the bending. I forgot to incorporate that slide. I do have that, but we do the picture frame shearing and the bending of the fabric as a characterization. And then we try to predict the dome shape. Then the L bracket to get that spring incorrect is also one of our like the validation case to use. So I would say we don't really have there's no STM standard. There's no single way to do it, but we aim to make sure that the input material property, we can measure that in lab. Now we grab a number, right, arbitrary, and then we get a example, like a simple geometry to validate, and then we get another more complex case to predict. So that's usually is the procedure we follow.
Oh, okay. Yeah. Thank you very
This is an
much.
excellent question. I would say unfortunately, that's actually one of the challenge we are facing is there's no single standard. There's no really standard to do that.
Okay, yeah, thank you very much for the insight. I think we
Sure.
have Zarin. You can go ahead with your question.
Yeah, thank you for the nice presentation. I had the question regarding the simulation work. So you mentioned you are using the genetic algorithm. I wanted to know that how sensitive are the optimization results to variations in input parameters, such as material properties. Like you mentioned, you are using carbon fiber, but what if expanded graphite or something like that is used? And also, you have mentioned the digital twin integration. And if you please discuss any case studies where digital twins have like significantly improved the manufacturing performance. Thank
Sure,
you.
thank you so much. I think it's a excellent tough question to answer. So I'm not expert in the design optimization, so I cannot really answer you're probably not the give you a very good answer for your question. But the fact that we are so if my understanding is if you so we the framework is based on the physics base, so it doesn't matter if it's a carbon fiber or other types of fiber, or we change a polymer. We actually have do that with a different type of the polymer. I mean, that is not a big deal. But so I think this is a two question, and we never combine. We do sensitivity analysis for the uncertainty. Oops. So we do uncertainty quantification with to understand if there are variability of the materials, right? It's a Gaussian process model, so we vary all the material properties. Say, hey, if we each of the material properties can have certain variability, and also account for the modeling uncertainty, and it allows actually to get a prediction on the how the uncertainty propagate in the manufacturing. We didn't incorporate uncertainty into the optimization framework, which I think is a very, very neat question you are asking for, because I'm not really in the design. I may need to consult some of the expert in the design optimization incorporating uncertainty. So I learned that when I was a student, but it's just a textbook study about how to incorporating the uncertainty into the design optimization. So I think this is a very interesting question, and we may need to think about to incorporating that into the optimization framework. Can you repeat your second question?
Oh, thank you for the first question's answer. The second was I wanted to ask, like, if you could discuss any case studies where digital twin have like improved the manufacturing performance.
That's very interesting question. So I do like one of my if you look at the early slides, that's not typical my work, but it's a in general the work with my colleague that doing those digital modeling. So there's one very impressive work is my colleague now Professor Rossio, and also Professor Pipes, who is our center director, working with Thermood to do this large scale additive manufacturing. So if you are playing around with your like a little printer, if you download a model from online and then when you print, especially if you want to print a screw and a nut, most likely it won't fit, right? And you will see all the comments saying, "Hey, it may like I print with this particular printer that will work. If you print from a different printer, it may not work." It's the fact that we know that when during the additive manufacturing, it print from a very high temperature, right? And it'll cooling down, so it will get dimensional change. I mean, if it's a hobby like it doesn't matter, you just send it or you just resubmit a model. Usually those printing are pretty cheap. But that's not the case if you are building those larger tooling, right? The cost will be huge. So they actually demonstrate that using the simulation framework allow people to know the dimension accuracy and help to improve the printing process for the mold. If you see I don't know, it is pretty fast moving, but you can imagine how big it is when you are trying to print parts like this, and the simulation will be very, very important to do. Like another example I also list on the very beginning is the collaboration with Boeing and also Dassault System on the high rate playlist system. I'm not sure if this is a movie or it's a static slides. It used to be an animation we can play. Is Boeing was very, very conservative about using thermoplastic composites because all the manufacturing challenges. So this is also some of the simulation work that is trying to demonstrate to the Boeing team how to use digital twin, how to use model-based engineering to do the part design. So it's still that is still on the I would say proof of concept, and I don't believe Boeing eventually be able to drive this technology at this time. But when nowadays big decision being made, simulation play a critical role.
Thank you so much.
Thank you.
Okay, thank you. And if anyone has any question, Yeah, I think I would leave it for Professor Farouk for question or comment to like our speaker.
Thank you, Dianyun.
Hi.
This was a very intriguing presentation, and it was far-reaching. And what I found particularly interesting was that there are a number of open research issues that you touched upon in terms of it's not settled yet. And in particular, you mentioned the use of a digital twin. And I was wondering if you could share some ideas about what you have in mind for a digital twin, because every Tom, Dick, and Harry talks about a digital twin. I'm interested in what your take on that is.
Yeah, so I yes. So I think we want to always try to build a digital world about everything nowadays. But the fact that is once you compare with the real experiment, what we see in the lab, it is always different. So something in my mind is this digital tool should give us a fairly early prediction about what's going on or anything wrong or something we should do the rework at the early stage. So for example, when we are doing the infusion process, we have been seeing so many defects that can happen even with our small coupon, because you can imagine when the parts become longer and longer, the infusion itself will take very long time. So if we can have a simulation, but at the same time, we also have the sensor data, if the simulation can be efficient, can be very efficient, then once we look at the sensor data, we immediately can predict what's going on or something went wrong that we should stop, we should rework, or we can immediately predict what will happen in the future. So this is one thing that we've been looking into, so that we need to make those physics-based simulation more efficient using the AI machine learning tool. Is something we have been trying to figure out how to do it, how to incorporate those physics-informed simulation into the physics-informed machine learning model, right? To make it more efficient, so that when we are doing the manufacturing process and we got the sensor data immediately from the sensor, we can predict if there's a leakage, if there's a race tracking, if there's a void, or there will be dry spots happen, and we can do the rework, or we can just stop it on the early stage. And this is just example of the infusion, right? The curing will happen at the same time. If we look at the data, for example, we measure from the sensor that we see those shrinkage data being show up at the different crucial locations, we can quickly predict if the parts will have the deform into a shape we like, or if it start to deviate, and we can do some of the change. And also the work with the optimization is with the digital way to mimic the true manufacturing process. We can make the whole, I mean, especially for the composite manufacturing, if we use different geometry, we use the different part geometry, different material, or like different fiber orientation, how we actually being design a manufacturing process that can reduce the defects and to improve the efficiency. So I think it's penetrate multiple directions.
So what you're really looking for is simulation to help you predict behavior.
Yes.
Okay, thank you. Because a digital twin has a different meaning to me.
Right, I agree. I agree.
So thank you. So thank you very much indeed. Thank you all. And do reach out to Dianyun with further comments, further questions. William, Sudikur, Rodney, Zoreen, Norian, all the best. And we wish to see you again. I will share the link, and then we can take it from there. Bye. Be happy.
Thank you for
Thank you.
having me
Thanks.
back.
Thank you,
Thank you
Daniel.
very much.